Hello, everyone. In this video, I would like to share some cut and paste methods of investigation regarding areas of squares and right-angled triangle, which may support the learning of Pythagoras Theorem. And I will also talk about some pedagogical principle behind, based on a book that I found, a very old one, written in the 18th century. It's about geometry and geometry teaching. Okay, and now let's start with some drawing in the Polypad here. Right, you can use the custom tool to create shapes, just like quadrilaterals or right-angle triangle. So to start with, I would like to make a square like this, okay? And you can also change the transparency so that you can see more clearly the grid below it, okay? And now I can start with this question with Form 2 students and before or after the learning of Pythagoras Theorem. And let's think about the area of this quadrilateral. I hope that they can see that this is also a square, even though it's not in the standard position, but it's also not too strange for most of them. Right? And they can think about intuitively how to find the area of this square, which they might also experience in the primary school, right? By just simple cut and paste. And so here it is one way that you can cut it. And so you can cut it vertically and then horizontally. So now you have 4 pieces, very nice one, which you can also reassemble to make 2 squares. So let's see. Maybe we change the color to distinguish the upper part. We're going to move it later. Okay, now you can see my translations, okay? And so sliding the pieces below, then you can find 2 very nice square, which can help you to tell the area immediately. Now, this method, of course, may not be immediately noticed by all students in the class, but if you're given time for some quick discussion, and usually 1 or 2 or even a few of them will be able to suggest this kind of method for this very special case of a square in this orientation. Okay, and so this is the starting point of talking about how to transform a square like this into another form, which can help you to find the area or tell the area more easily. Right now, the next one will be more challenging. Right, and I also draw a square on the grid. Okay, and so they can first think about whether this is also a square. Now, to start with, you may even also use the utensils in the Polypad. Actually, you can find it here, okay? And we have a protractor for you to measure the angles, right? Or use the set square, okay? Then you can also easily check the angles here if they prefer something more concrete, okay? To find out or to verify that this is a square. But of course, I hope they will also appreciate some reasonings like this. So we can fit a right angle triangle below it, make good use of the provided square grid. Okay, so I can turn it into another color. Okay, and in this way, you can argue or discuss with the student how you can fit 4 copies of this right angle triangles around the middle by green shapes or quadrilaterals. Okay. And this may also help the student to confirm that the green one is a square. It's also a square, even though we call it a tilted square, right? Not in the common or the very typical orientation. Okay, so we can put aside this one. Now, after confirming that this green one is a square, then we can go on to talk about its area. Can we find the area of this green square? Actually, it's not really so difficult, right? Particularly if they have the square grid, then they can use the standard way of cutting it to find or to calculate the area. But you may also, however, suggest some method of following the previous example, okay, using some cut and paste idea to turn it into a shape with, which can allow them to easily recognize the area, or even without numerical calculation. All right. Now, how we do it? Let me put aside this right angle triangle for the time being. Remember how we do the cutting at the in the beginning, okay, with one vertical cut and then a horizontal cut through the vertices. Let's try something similar. So I cut, first of all, I cut it vertically through the vertex on the top. Okay, even though we don't have two equal parts, all right, however, we can still continue somehow in this way, cutting the left and right part horizontally, also through the vertex. Oh, I better try again. Cut it more accurately. Okay. All right. So you can see I have also two triangles, right angle triangles above. And let's color it in a different way, or more or less in this way. Well, then can we make use of this triangle? Okay, perform some kind of transformation, and more or less in the same way. Remember, originally we do this sliding. Okay, so let's just try the same thing. Yes, and they may see that it really works. Okay, and you can try to highlight that this is a square, and here also another square on the right, even though they are not identical. Right now, you can use the rectangular frame provided below. Right, and use the black one to highlight the two squares that they may see or they may recognize. Okay, and in this way, then you can also tell the size of the original green tilted square, right, by looking at this newly formed square, right, and then hoping that they can also tell the square area immediately, and appreciate that we don't need too much or any calculations involved in this process as well. Okay, so this is the basic ideas of cutting and rearranging. And going back to the original square, you can also now compare and then notice how the transformations can be done, okay, in a very intuitive manner. And of course, meanwhile, you can also discuss with the students why we have two congruent right angle triangles here, right, which allow us to do this reassembling in an easy way, right? So it depends on how much you want to discuss with the student, right? They can also try to spend some time on understanding more about these properties of this figure, right? And now it comes to the point to conclude a little bit, right? And these questions allow us to talk about a tilted square originally, and with some transformation, we obtain the two other square in the standard position, which allow us to tell the size of the original one. And actually, you can also further reposition the two squares in this way to let us know that it is actually fitting the right angle triangle at the beginning, okay, at one corner under the original tilted square. And it also let us know how the two resulting square actually had their size closely related to the legs of the right angle triangle. Okay, now, of course, then up to this point, you will notice that it can be some kind of introduction to the Pythagoras theorem, particularly how we see there are certain special relations among the sides of a right angle triangle, right, if we consider the associated square building on the sides. Okay, and up to this point, let me go back to one of these very interesting books in the Internet Archive, right, which shows this idea. So you can see on this page, this is a book in the Internet Archive, all right, written by this mathematicians, Clairaut, okay, and you can see that it is a book actually in the 18th century, right, 1740 something, but this one is an English translation, so it's published later, right? But the original book is already published actually more than 200 years ago. And now you can find in the Internet Archive, and you can go to any pages, right? So you can see more pages if you click on this one, and then you can access all the contents of this book here. So I'm referring to one part, okay, where the author tried to explain this exploration, based on his more typical case or more special case of a square, and then go into a more general case of a tilted square, and put it and using some transformation that I explained to turn it into two other squares so that you can tell the area. And based on this, later on, you can see the author make use of this to talk about the Pythagoras theorem. His main point is to suggest right, the process of discovering the theorem, not simply stating the theorem, right, but try to argue in what way that based on some intuitive exploration, right, then you can appreciate the relation between the sides of the right angle triangle in terms of the square. If you look at the details, it's not exactly the one I show in the Polypad, because the author used rotation of the right angle triangle, not the sliding. Okay, so I modify the ideas a little bit. However, I try to follow the same principle of using a special problem, and then in order to initiate, okay, this kind of discussions about the area, and even going on to introduce the Pythagoras theorem in a reasonable way. And I can even share with you in the beginning of this book how the author explain his pedagogical principles, okay? And so you can see in the preface, and how at the beginning the author explained very clearly and his suggestions about the teaching of geometry, which is rather special at that time, right? And in the 18th century, because he liked to argue that the student should learn more intuitively, okay, from experiments or from different kinds of reasoning, leading them to know more about the properties, okay, or the ideas behind the geometry, instead of starting from axioms, formal procedures or proofs, or theorems. Right? Now, this is rather different from the traditional way of teaching geometry at that time. Even nowadays, I can see that this is not readily accepted by a lot of teachers, or really appreciated by a lot of teachers, right? So these are very amazing ideas at that time. And you can also further down find the other part, okay, in this page, where the author explained around here about, I think, okay, how he suggests that the discovery of the idea can be introduced or incorporated in the teaching and examples well before the theorem is formally stated, right, for the student, so that they know more, maybe more easily, okay, the line of thoughts or the reasoning involved, or kind of observations that can help them to appreciate the ideas and the properties. So which is demonstrated by the previous examples of the Pythagoras theorem and the page I show you, and also in this Polypad activity. So I hope that you can find this example useful, particularly how we can encourage some kind of exploration and drawing attention to the important properties and relations, particularly make use of the student, their own intuitions and observation, rather than because of only formal procedures in proof and reasoning. Okay? Let me continue a little bit and showing the other thing we can do in the Polypad, okay? And in fact, you can also try to imagine how the same ideas can be applied to other tutor square, and also using other kind of cut and paste methods as well. Okay, now let's clear this part. Perhaps we can try another square. Let's see. Okay, and we may have a bigger one like this, perhaps. Okay. So I go on to make another tutor square, right? Something like this. And also change this to transparency. Okay. And you may also create a triangle underneath. And also highlight that we are interested in this triangle as well, okay? So particularly, we can now repeat the procedures, but now let's state the problem in a different way. So if you're given a right angle triangle in this square grid, then you can see the length of the legs, okay? The two sides 2 and 5 here, all right, which is quite obvious to student. But what is not so obvious to student, of course, is the length of the hypotenuse, okay? And there's no simple way for them to find out this length, okay? But using the previous exploration, you notice that we can tell the area of the square, okay, on this hypotenuse. And through the area, we can find the length. Now, this is not a simple idea for many students, right, in secondary too, right, because based on the experience in primary school, what they usually do is to find the area for square based on the length of the square, right? Now we are doing something exactly in the opposite direction. That means we find that it is easier to find the area of a square in such occasion. And in fact, it is difficult to find the length, all right? However, we can use the area to find the length. So the whole things about Pythagoras theorem can be built on this kind of discussion. I drawing the attention that now we're interested first in the area, and exactly because we also want to find the length in this special case of the hypotenuse of a right angle triangle as well. Okay, so before we move on, let's try to clarify our intention of studying the squares building on the right angle triangle. And so now we can repeat the process again, right? How to cut this square, and in case they forget or maybe they may not follow exactly the previous method, let's remind them that we expect the result to be something like this. Okay, so we assume that the green square should be transformed into two square based on the other legs of the right angle triangle. That means this square of 4 and this square of 25 units, right? And if you still remember, we actually rearrange it in this way, right, so that the two square can be placed underneath the green square, and then allowing us to do the cutting, right, and then rearranging it. So let's put aside this right angle triangle for the time being, concentrating on how to transform this green square, okay? And let's see how we can follow the same method, cutting it vertically down this vertex. And then now, in fact, the lines of the square already suggest how we can go on to do the cutting, okay, on the left and on the right, okay, particularly because of the grid and also the two imagined, okay, square that we start with. Okay, now perhaps you can also try to change the color a little bit. Okay, right, so now you can nicely slide the triangles to confirm that it really is the same as the two square, right, at the beginning based on the size or the legs of the right angle triangle down below. Okay, so this is one way that we can demonstrate again the transformation of square, at the same time to let them feel that, okay, perhaps this is a general method, right, that they can try for different tilted square in this way. At the same time, then we can find the length of the hypotenuse because we know the area of the square on the hypotenuse. Right? And finally, let me show quickly another simple way to reason about the area. Okay, as we mentioned earlier, let's go back to this original square, and you can also join it again. Okay, to make it a big original square. Okay. Actually, you can also quickly surround the square by the right angle triangle below it. So let's make 4 copy again. Okay. Maybe you can distinguish it by different color, but they are the same triangle. Okay, and this figure can also help us to find out the area of the green square. Right? Now here we're surrounded by bigger square, particularly by enclosing it with the 4 copies of the right angle triangle at the beginning and the top in the bottom right. Okay, and we can also draw a big square to remind us this whole thing. Okay, and closing the green square. And now we make a copy of this figure. Okay. Trying to rearrange, yes, copy the whole thing and then carefully drag it to the right for comparison. So let's take away the middle square, but we can now rearrange this 4 pieces of triangle, okay, and then try to check that what's left behind inside the big square, right? The empty space of the 2 easily recognized square, which should have the same area of the green square because we just removed the green square and then rearrange the original triangles around it. So that can also be a very intuitive and simple way to argue how to find the area of the green square in a very easy manner, right? If they can follow this arguments of cutting or maybe simply replacing, right, or dragging around the pieces. Okay, and finally, maybe you can actually draw the square around this, perhaps. Let me remove this one and go back to the drawing tools again. Okay, and we can also have this kind of square. Oh yeah. Okay, another one, perhaps. Yes, you can use a rectangle tool. Okay, in order to fill it and make it easier to make the comparison. Right. All right. So that may that may also be useful, but this is another way of talking about the area of the square and following a very traditional way of reasoning with these triangles and areas, and also regarding the Pythagoras theorem. All right, so maybe I finished the demonstration here. I hope that the tools here can be useful for generating problems and discussion with your students, and at the same time to think about some arrangement, okay, in talking about the mathematical ideas, right? And particularly referring to the pedagogical principles I mentioned, according to the books I discussed in this video as well. Okay, thanks for watching, and follow the links below, maybe to find my files. Okay.